Hello, welcome to Maths with EJD. In this video, we'll talk about correlation again, talking about Spearman's rank correlation this time around. So the Spearman's rank correlation coefficient is denoted by rho, or if you like, RS, is a non-parametric measure. It's a non-parametric measure of the strength and direction of the association between two ranked variables. So here ranking comes into it. So unlike Pearson's correlation, unlike Pearson's correlation, which assesses linear relationships, between continuous variables. Spearman's correlation is based on the ranks of the data rather than their raw values. So it is useful for ordinal data. So in case you have ordinal data, you should think of Spearman's rank correlation. So it is useful for ordinal data or when the relationship between variables is monotonic but not necessarily linear, So the formula for Spearman's rank correlation coefficient is R equals 1 minus 6 summation d I all squared divided by n into n squared minus 1. So here, n is the number of data pairs, di is the difference. So it's the difference between the ranks of each pair. So ranking is the key thing here. So let's look at some examples. Say example 1. For positive correlation. So suppose we have the following data showing the rankings of students in two subjects, say mathematics and English. So here we have students rank in maths, rank in mathematics. Let me do it this way to save space. Rank in mathematics, then rank in English. In fact, I can save space, right? Starting from the math thing. Rank in mathematics better. Rank in English. Then we have difference. That is DI. Then we have DI squared now. The square of the difference in ranks. So we have student A, B, C, D, and E. Actually, the if you're in an exam situation, you just be given the first three columns: student, rank in math, and rank in English. That's also the DI and DI squared as where the calculations should actually start from. So let's have those. So for rank in math, right? Student A is first, student B is second, student C is third, D is fourth, and E is five. But for their rank in English, student A is actually second, while student B is first, student C remains third, student D is fourth, and E is fifth. So talking about their differences now. So it's like so just subtract directly. So 1 minus 2 is minus 1. 2 minus 1 is 1. 3 minus 3 is 0. 4 minus 4 is 0. 5 minus 5 is 0. So that makes things pretty easy. So if when you square, so okay, I think I want to use another marker to show that that's where your calculation starts from. So 1 minus 2 is minus 1. 2 minus 1 is 1. 3 minus 3 is 0, 0, 0, like that. So this is 1, 1, 0, 0, 0, basically. So um so we have calculated the difference in ranks like that, and we have squared the differences. So now we need from the formula, right? We need the sum of all the sum of the squares and all that. So again, let's call the formula. Rho is 1 minus 6 summation di all squared all over n into n squared minus 1. N into n squared minus 1. So di, summation of di squared, that summation of di squared will be just 2, if you add up all of that. So di is 2, then n is 5, I believe. Yeah, that's 5. And then rho now is equal to 1 minus 6 times 2 all over 5 into 5 squared minus 1. So rho is equal to 1 minus 12 over 5 into 25 minus 1. So rho is equal to 1 minus 12 over 5 times 24. So 12 here is 1, 12 here is 2. So rho is equal to 1 minus 0. Okay, I think I'm jumping. So 1 minus 1 over 10, So that is rho equals 1 minus 0 0.1. And rho is 0 0.9. That's a strong positive correlation. So let's interpret that in that context. So the Spearman's rank correlation coefficient is rho equals 0.9, which indicates a strong positive correlation. This means that as students' rankings in mathematics increase, their rankings, their rankings in English also tend to increase, Okay, so that's the first example. We have time for more. Let's take another example, say example 2, that demonstrates negative correlation, going by Spearman, negative correlation. So now we have another set. So consider another set of data where students are ranked in history and geography. So you have students A, B, C, D, and E. 5 again. So you have rank in history, and then you have rank in geography. So normally this is what you have as your original data. So this is 1, 5. This is 2, 4. This is 3, 3. This is 2, 2. And this is 5, 1. Of course, it's obvious even from the data, but things won't always be this obvious. So you still have to do the work. So here now, we need the difference, which is di. Then we need the square of the difference, that's di squared. So the difference di, 1 minus 5 is minus 4, 2 minus 4 is minus 2, 3 minus 3 is 0, 0, 4 like this. So square that as 16 plus 4 plus 0 plus 0 plus 16. That's 20 plus 16, which is 36. So summation of di squared is 36. Is it 36? Should yeah, that's 36. How come it's 40 here? It's 30. Okay, that's my fault. Just wondering. So this part is rank 4 actually. This is rank 4. So that 4 minus 2. 4 minus 2. Okay. 4 minus 2 is 2. 2 squared is 4. So that's summation of di squared is 40. So that's when you square all of that, you can now say therefore, of course, rho or RS is fine. Spearman rank, that's 1, 6 summation di squared all over n into n squared minus 1. So again, we have summation di squared already is 40. That's when you sum up the square of the differences. Then n is in 5 pairs again. So that rs now is 1 minus 6 times 40 divided by 5 into 5 squared minus 1. So rs is equal to 1 minus 240 divided by 5 times 5 squared is 25 minus 1. So that rs is equal to 1 minus 240 divided by 5 times 24. 5 times 24 is 240 divided by 2, which is 1 minus 240 all over 120. So rs is equal to 1 minus 2. So the Spearman's rank correlation coefficient is actually minus 1 in this case. So the interpretation is that the Spearman's rank correlation coefficient is rs, which is equal to minus 1, which indicates a perfect negative correlation. This means that as students' rankings in history increase, their rankings in geography decrease in a perfectly inverse manner. Yeah, so we have those two examples. Let's go to test for significance for all this. So let's do this interpretation and significance of correlation coefficients. So one, have range of Spearman's rank correlation coefficient. So first of all, we have RS or rho ranges from -1 to 1. So don't forget, it can be, we can say it's rho or RS. I started out with rho at some point. Yeah, this should be RS here. So don't get confused. Oh yeah, I already said it. Rho or RS, yeah. So either one is fine. So RS ranges from -1 to 1. So that when we have RS equals 1, that is perfect positive correlation. Perfect positive correlation. Okay, that's as one variable increases, the other also increases. Then we have RS equals -1. That's perfect negative correlation. So as one variable increases, the other decreases. And lastly, R is equals 0. So in that case, no correlation. So here, there is no apparent, relationship between the ranks of the two variables. So we go for significance testing now. To significance testing. So how do you see, how do you determine if a particular correlation coefficient is significant? So to determine if the observed correlation is statistically significant, we can form a hypothesis test and the first thing is talk about the null hypothesis. Null hypothesis, which is H naught, and that is there is no correlation between the two variables. That means that rho is equal to 0. And then we have the alternative hypothesis. Call that HA or H1, anyone you choose, so that that will be that there is a significant correlation. There's a significant correlation. So rho is not equal to 0. For large samples, and here large sample is like n greater than 10, the test statistic can be approximated by what we had before, for that's t equals rs square root of n minus 2 over square root of 1 minus rs all squared. So this follows a t distribution with n minus 2 degrees of freedom. So based on the t value and the degrees of freedom, we can check if the correlation is significant. Right? So let's talk about how to interpret correlation coefficients. interpreting so first we can have strong correlation, strong correlation. So that's like something between 0.7 and 1.0. That's if the absolute value of RS or rho, let me use rho in this case, if the absolute value of rho is closer to 1, the relationship between the two variables is strong, and changes in one variable are strongly associated with changes in the order. That we can have moderate correlation. That's when you have something like absolute value from 0.1 to 0.4. So this is a weak correlation, which indicates a slight association between the variables. Then, of course, we can have no correlation. No correlation. So, we've been doing 0.1 to 0. So that's, of course, just zero, straight zero. So in this case, we can say no relationship. And we can, of course, use the kind of classification we had for Pearson. That also works. No relationship between the variables, meaning changes in one variable do not predict changes in the order. Then let's talk about practical significance of all this. So practical significance. So what is the essence of high correlation, for instance? High correlation. A high Spearman's correlation coefficient, rho or RS, in contexts like educational performance, may suggest that Students who excel in one subject, students who excel in one subject also excel in another. Then we talk about negative correlation. So this should actually be okay. Well, I mean, negative correlation in short in this case would be something like that, that in business, a strong negative correlation might indicate that an increase in one factor like price, e.g. price, leads to a decrease in another, e.g. demand. So as price increases, demand reduces. Then we go for zero correlation. Zero correlation. So here, if no correlation is found, it suggests the factors being compared operate independently. So finally, Spearman's correlation, Spearman's rank correlation is especially valuable in cases where the data do not meet the assumptions of Pearson's correlation. So Pearson's correlation are basically for numerical or continuous data. So once that condition is not met, maybe all you just have is ordinal data, and you have to think of Spearman's rank correlation. So it did not meet the assumption of Pearson's correlation, such as non-linearity. So if the data is non-linear or ordinal, non-linearity or ordinal data. And with that, we come to the end of this. So if you have not subscribed to this channel, please do that and hit the notification bell so you can always get notified each time a new video is released. And comment, let me know if you want me to solve a problem or teach a particular topic, and like and share also so that more people can have access to this. See you next time.